And just when you thought you knew everything there was to know about the parabola, we're going to dig a little bit deeper, and we're not going to turn it upside down, although we will do that, but actually we're going to turn it sideways in this video. Let's see some details about the parabola. The first thing we see here is are two forms of the equation for a parabola that we are pretty familiar with. The first one is sometimes referred to as vertex form because it's very easy to extract the vertex of the parabola when the equation is written in this format. The coordinates of the parabola are h comma k. And you do have to watch out for a sign change on that h value. If it said x minus 2, your h value would be a positive 2. The second form is pretty much in the form of a quadratic equation, okay? And that's the one where if our y value was 0 and we were trying to find the x values that would cause the right-hand side to equal 0, we could use the quadratic formula. But as far as graphically interpreting these equations, we're talking about the parabola. If the leading coefficient, the lowercase a value in either one of those two equations is greater than 0, then our graph is going to open up. And by open up, I mean concave up like this one. If a is less than 0, then the graph opens down. Or I might say concave down instead of opening down. The vertex in number 2 here, if our equation is given to us in this format, is h comma k. And when the equation is written in that second format that you're seeing sort of at the top right, that traditional quadratic equation kind of a setup, the process of finding the vertex is a little bit more involved. Okay, it's a lot more involved, but it's still pretty easy. It's sort of a two-step process to find the coordinates of the vertex. The first thing that you do is find the x-coordinate, and you can find the x-coordinate of the vertex by taking the opposite of this b value and dividing it by twice the a value. So we're going to say that the x-coordinate is the opposite of b divided by 2a. If you wanted to find the y-coordinate of the vertex, you would take whatever that x value is and plug it back into the equation in place of x and calculate y. Something that we're seeing in these illustrations that's not mentioned, I don't think, anywhere on this page, is that vertical dashed line that has an equation x equals h. And that is referred to as the axis of symmetry. And the axis of symmetry is obviously where the parabola would sort of fold over onto itself. And the equation for the axis of symmetry, since it runs right through the vertex, the equation is x equals h. Now the actual definition of a parabola that you might not be aware of is that it's a set of points, all of which are the same distance from or equidistant from a fixed line, which you can see in this diagram is called the directrix. It's a vertical line there. And a fixed point called the focus, and you are familiar with graphs having one focus or really two foci in the case of an ellipse or a hyperbola. But here with a parabola, we're only going to have one focus, so we'll be in the singular there, and you'll notice that this distance d2 is always going to be equal to this distance d1, no matter where we put the point. So if I put my point here, I draw my dashed line to there, and then a perpendicular dashed line over to the directrix. The length of those two lines must be the same. Now that also means that if I drew or picked my point to be right here, the vertex of the parabola, the distance from the focus over to the vertex is the same as the distance from the vertex to the directrix. And we're going to, well, you can actually see it here in this diagram, the location of the focus is p comma 0. And we'll talk about that p value in a moment. That's going to be a specific number depending on the equation that we're working with. But this distance here is p, which means that this distance is also p, because d1 has to equal d2. Any point that we pick on the parabola has to be the same distance from the focus as it is from the directrix. So the distance from the vertex to the focus is always going to be the same as the distance from the vertex to the directrix. And the parabola is always going to be opening away from the directrix like this and wrapping around the focus. So these are sort of basic standard forms of the equation for a parabola. We're presenting these differently than you've seen them before. You're used to something that looks more like, I keep trying to write with the eraser and it doesn't work very well. You've seen things like y equals 3x squared plus 2 maybe. Or the y is isolated on one side of the equation instead of the square being isolated on one side of the equation. So these are a little different. It'll take a little bit of getting used to. I'm sure you can handle it. There we are. Now, the illustration that we see on the left, this has our y value being squared. And the one on the right has our x value being squared. The diagram on the right is the one that we're most familiar with. We're used to parabolas either being concave up or concave down. And you'll notice some familiar characteristics to this equation. There's a y, there's an equals, and there's an x squared. So if you see an equation like this and you're trying to determine, is it going to be concave in the up and down direction or in the side to side direction? If it has a y and an equals and an x squared, then it's going to look a lot like the parabolas that you're used to seeing, concave up or down. And if it has an x equals a y squared, then it's the other one. It's opening side to side. These equations, it works in the case where you have a parabola that's passing through the origin. So if the vertex of the parabola is at the origin, those will be the equations of the directrix, depending on which of these two versions of the equation that you're working with. As you know, I like to take a lot more sort of commonsensical approach to determining some of these things based on my own diagrams. So I'm going to continue doing that, but realize that these illustrations and things that are provided here are indeed true. And if you want to commit those to memory, you're welcome to. I just ask that you consider an alternate perspective. There's another sort of unfortunately named component of the parabola in the form that we're looking at it, and it's called the lattice rectum. And this unusual line segment is the line segment that is parallel to the directrix. So I'm not even reading what's in that blue box. You can read that if you want to. You'll notice that the lattice rectum is parallel to the directrix, which is down here. And we talked already about this distance being p and this distance being p. Well, this distance right here is always going to be 2p, as is the other half measuring 2p, which means that the lattice rectum is always going to have a measure of, excuse me, 4p. Doesn't matter if it's in this, excuse me, doesn't matter if it's in this diagram or the one to the left, lattice rectum length 4p. I love this illustration. I like seeing all of these different lengths interacting with each other. You take the first one, which is a p, you double it, you get the 2 p's, you put them together, you get the 4. I don't know, something pleasant about it. I suppose I can point out also that for this particular equation, the x equals 4py. It's that coefficient on the linear term, which is the y term here. It's that coefficient that's going to help us calculate our p value and 2p and 4p. In the other version of the equation, which will come back in a moment as soon as I plug the iPad back in. There we go. Here you can see that the 4p is a coefficient on the x variable, and so we'll be using that in order to find our p value, which is going to help us find the focus and the directrix and the length of the lattice rectum. So far we've been through a couple of pages of notes and we haven't seen a single number yet. So we're very happy to arrive here. And let's see what we can do with this. This original equation has an x equals y squared format instead of y equals x squared. So I know that this is going to be a sideways opening parabola. I'm also pretty confident that this parabola is going to be opening in the negative horizontal direction because of that negative a value, so to speak, or that negative coefficient on the linear term is another way to say it. So if we sort of match this up with the idea of y squared equaling 4px, then we can see fairly clearly, I think. If you want to highlight it or something, you're welcome to do that. That the negative 12 is equal to 4p. And so we can say that negative 3 is equal to p. So this is a parabola that's passing with its vertex at the origin. And we know that it's concave in the horizontal direction. And it's going to be concave in the negative horizontal direction because of the 4p value is negative. There we go. And let me just show you how this plays out using our p value. So I know that let's see, I'll use purple. I know that my vertex is at the origin, and we'll work with some parabolas, or at least one where the vertex is not at the origin. But for the moment, I'm plotting a point at the origin. I know that it's concave left, which means that, let's see if I can do this. Oops, the other way. There we go. Since it's concave in this direction, I know that the lattice or the directrix needs to be behind it. So if my parabola is opening this way, my directrix needs to be over here. I can just throw that in there for the moment. And I know that the distance from the vertex of the parabola to the lattice rectum needs to be 3 because my p value is 3. So just by drawing this quick sketch, I know where my directrix is going to be. So concave left. So I'm coming back over to here. So concave left, and I think we should also use that to know that so concave left and let's say directrix maybe right of vertex. Which is why I'm drawing the vertex here. I know that I'm concave to the left. Since it's concave left, I know that the directrix will be to the right of it. I drew that quick sketch so that we know, and you could draw just that tiny little diagram over here. Concave left, directrix to the right. Dashed more than dotted. There we go. Okay, the other thing that we know is that the focus will be p units, in this case, to the left of the vertex. So again, I'm really knowing that because of the sketch and my knowledge of the orientation of the parabola. So you can see I drew in a little vertex right here inside of my parabola. Little focus inside of there, okay. And so let's plot the focus also at -3, 0. And then we have the lattice rectum, which we know has a total length of 4p, which means we're going 2p up and 2p down. So now I will move 2p above and below focus for the endpoints of the lattice rectum. All right, so off to the graph, starting at -3, 0, I'm going up 3 and then up another 3, so I'm at +6, yep. And at -6, With these 3 points, excluding the focus, I can now draw a pretty reasonable approximation of my curve. I'm going to start at the vertex and come down and pass through that focus, or through that end of the lattice rectum. And then I'll do the same in the upward direction. Let's see if we can fairly smoothly get out through there. We've got ourselves a good looking parabola. If you'd like to label your graph a bit, we can say that 6 is equal to 2p. It's really the so I'm using p. P is actually -3. So the distance that I just blocked off is technically not 2p, it's the absolute value of 2p. And to be precise, we should put absolute value bars around that. The fact that p is negative is more valuable if you adhere to the sort of printed instructions that appeared a little bit above where we are right now. But because I go very diagram-based, I don't really care that the p-value is negative. I know that if my parabola is concave left, then the directrix is going to be below it, or sorry, to the right of it. If my parabola is concave up, my directrix is going to be below it. If it's concave to the right, directrix is to the left of it. If it's concave down, directrix is above it. So I just kind of have those things in my head, and my hope is that you'll come to a level of familiarity with these graphs that you won't really need to worry about whether p is positive or negative. You can just draw yourself a little sketch and then build yourself a more precise graph from there. Find the standard form of the equation of the parabola. So our focus is at 9, 0. So I'm drawing just a quick little diagram here. Focus is at 9, 0. Directrix is at -9, which means that my parabola is, the vertex of my parabola has to be halfway between the directrix and the focus. Has to be. And I know that this is my p-value, or I could have done that out here. This is equal to p also, which means that this distance, it also means that this diagram's not drawn very well, that this is equal to 2p, and this is equal to 2p, which means that this is equal to 4p, and p is equal to 9, because we were told the location of the focus, 9, 0. This is a sideways opening parabola. So these are the kinds of things that I struggle to know exactly how to write them down for you. Really, I want you to write them down in your own words, but I'll do my best. It's concave right. Therefore, I know that it's of the form not y equals x squared, but x equals y squared. And we know that 4p from our diagram that we've drawn is equal to 4 times 9, which is equal to 36. Therefore, we can write our final equation as y squared equals 36x. I didn't include this in here, but our not only is our parabola concave in the horizontal direction, which is why I knew that the equation was going to look something like this, but because it's concave in the positive horizontal direction, I know that my p-value really is positive. So concave right does tell us this. Where can we include that? This, let's say, I don't want to put it there. Concave right. Maybe down here we can put another sort of implication arrow and say that p is greater than 0. A little bit of a hack, but it works. All the information is there. If you'd like to restructure that, I don't blame you. Okay? Make sure that it's organized in a way that you can make sense out of it later. And then we start moving the parabolas around the coordinate plane. Let's look at this sideways facing 1 first. You can see the equation up here at the top. The y value is still being squared so that I know it's going to open, or therefore I know it's going to open horizontally. And the 4p is still there. So we'll be able to calculate our p-value. But notice that the y minus k and the x minus h are here, so our vertex is indeed located at h comma k. Same thing happens over here. The 4p is there, the h is there, the k is there, and the vertex is still at h comma k. So we have consistency there. Let's go down and see, oh, a matching game. I like these matching ones. Can I zoom out far enough that you could see all of them at the same time? Hopefully you're using these printable notes. So the equation at the top says, well, it has the y squared. Now we're used to seeing y equals x squared, so this must be a concave horizontal. So I see the y squared, therefore concave horizontal. I see that 4p is equal to 4, and 4 is greater than 0, therefore it's concave in the positive horizontal direction. All right, I won't write all of that out each time. I'm just going to say maybe concave left, right, up, or down. But you can write it out in whatever level of specificity you feel is most appropriate for you and for your own review later. So we know that it's concave to the right, positive horizontal direction. It must be our third graph down here. In our next equation, we have a y and an x squared. So here, x squared and 4p equals 4, which is greater than 0. Therefore, we'll say that it's concave in the positive vertical direction. Vertical can be up, vertical can also be down. So we do want to specify that it's concave in the positive vertical direction. Which means we're going up here. That's our matching graph. In the next one, we do have the x squared again, and 4p is equal to -4, which is less than 0. Therefore, it's concave in the negative horizontal, or sorry, negative vertical direction. Negative vertical, which is the bottom graph down here. And lastly, we have x equals y squared, so we're horizontal again with our concavity in the negative direction. So y is squared, and 4p equals -4, which is less than 0. Therefore, negative horizontal for concavity. Excellent. So a bit of practice identifying some characteristics that would allow you to draw a sketch enough to get oriented, and then you can fill in some details. So let's just do all of the things on this one. We need to convert this equation to standard form by completing the square. So we have to complete the square. We have to know our forms, and then we're going to graph. I'm pulling up my sleeves because we're going to get to work here. To complete the square, I'm going to push the y value, or the y term, and the constant term over to the right-hand side, I think. And then we'll complete the square on the left-hand side by taking the 6, dividing it by 2, and squaring it. So 3 squared is 9, and it's 9 that we will add to the left-hand side, but of course, whatever we do to the left, we must do to the right. So now we have x squared plus 6x plus 9 equals negative 8y minus 1 plus 9. If you want to put the plus, I don't know. I would probably just put a little note over here that says we're adding 9 to both sides. It's pretty obvious, I think, because we're only doing things one step at a time. Next thing I want to do is factor on the left-hand side, and I think I'll factor on the right-hand side also. Factor, factor. On the left-hand side, we've engineered this to be a perfect square. It is x plus 3 squared. And on the right-hand side, these add to make positive 8. So this really says negative 8y plus 8. And I'm going to factor a negative 8 out of those two terms and write this as negative 8 times the quantity y plus 1, y minus 1. So again, in here, this really says 8y plus 8. If I can make that look like an 8, it just looks more and more like a G. There we go. After you combine like terms, then I factored out the negative 8. Nice. Let's match this up with the correct format. This says x minus h squared equals 4p times y minus k, which means that the vertex h comma k is located at, I'll give you a moment. What do you think h comma k is? Tell me the coordinates for hk. Be careful, there are some sign issues that you have to watch out here for. Watch out for here. I'm a little backwards this afternoon. I don't know what's going on. It's the first video of the day. Just settling in. Our h value is actually a negative 3. It's the opposite of what it looks like, as is our k value. It's actually a positive 1. And of course, that's because the y values match up and the minus signs match up, and so the 1 must be the k, and it is positive 1. Great. Also, 4p is equal to negative 8, which means that p is equal to negative 2, or the absolute value of p is equal to positive 2, which is what I'm going to be using. So let's see, and are we given a graph here? Yep, we are. There's some graph paper for us. Our vertex is at negative 3, 1, so I will plot a point at negative 3 and then up 1. There we go. And my absolute value of my, oh wait, what's going on with concavity again? Let's look at this equation. This equation has x squared and 4p equals negative 8, which is less than 0. Therefore, it's going to be, it's a y equals x squared graph, which is what we're used to, so it's either concave up or down. But since 4p equals negative 8 is less than 0, it's going to be concave down. So therefore, concave down. this is certainly important. This deductive process is important. Surely the coordinates of the vertex are important, and having a p-value or the absolute value of a p-value, those are the ingredients that we need in order to draw our graph. So we're concave down at -3, 1. I need that information on the screen still. That is sufficient. And with a p-value of, or the absolute value of p equaling 2, I'm going to move down 2 units to plot my focus. I'm going to move to the right 4 units, which is 2 times 2, and to the left of my focus 4 units, that's 2 times 2. And then we can draw our curve. Not only can we draw our curve, well, I'm going to try to draw this curve. Half of the parabola is always easy. The other half, I have to move my wrist in a direction that it doesn't want to go. All right, little rough, but you get the idea. And again, if you want to label this, you are welcome to, but let's put one more thing on here first. Let's put the directrix. The directrix has a distance of p away from the vertex, and our p-value, or the absolute value of p, was equal to 2. So this is, we could just call it p. You can call this one p. If you want to, again, label this as 2p, and if you want to go all the way with it, you can put the 4p in here. That was not a requirement, but stating the coordinates of the vertex is important. Being able to talk about concavity is important, and you're going to need that p-value for sure to draw the graph, but also a question that you might run into is you might be requested to write the equation of the directrix. So this directrix is a horizontal line, and this point, and this point, and this point, and this one, and this one, and this point over here, and this one, they all have something in common. All those points have a y value of 3. That's how I remember how to write the equation of a horizontal line. It's the collection of points, all of which have a y coordinate of 3. So we could label this as directrix. There we go. It's been my pleasure to present to you the process for drawing something that we've drawn a lot of already, but we can be a little bit more specific with our diagrams here using this p-value and talking about the orientation of the parabola by way of the new format of the equations that we're seeing. So make sure you work enough practice problems that you're pretty agile and able to navigate these and orient these pretty quickly. They're not difficult problems, but unless you have a little bit of experience with them, you won't be able to answer questions about them quickly and accurately. It might be time consuming, and that might be to your disadvantage. So practice up, and if you're ready for the next and if you're ready to start the next section, you can click the link directly below me, and that will take you to the next video, which is about rotation of axes, and it's a good one. You might want to have a little power nap before you start that one. Either way, I'll see you again soon. Thanks.